Hi guys, welcome back to the channel, and this is Abhishek, and today we are going to solve a problem. So some updates from me. So since more than a year now I have been staying in China, and I'm working as a software engineer at Alibaba, and because of that I haven't been able to focus on the YouTube or anything else. So I thought maybe it is time that I start something again. So that is the reason I'm trying to make this video, and since last 1 month I have been trying to get out of that comfort zone of just going to the job and coming back and just traveling anywhere. So I thought I have gone rusty about my problem solving skills. So since a while I have been trying to solve some lead code problems and trying to get back on the concepts that on the course computer science concepts that I had forgot, like the data structures, the algorithms. I know that, but somehow I haven't been in touch with that. So today we are trying to solve a question from Leetcode. Like I was trying to solve, means I could solve it. There were some things I had forgot. I read about it, and then then I completely implemented by myself, and it felt good. And today I'm just trying to like do a screencast of the problem, and it will act as a memoir for me, because I don't want to forget how I solved it, because most of the time it happens that I personally feel good when I solve a problem, but then after a month or so, even when I look at my solution, I don't understand it. So it will act as a memoir to me, and it might not be too detailed, but at least it will give me pointers. When I look at it, I will understand. I hope it will give you all the pointers. It is just like let's learn all together. Uh, so today's problem I'm picking up is something called sentence similarity 2. It is available on Leetcode. I'll put the link below. You can have a look and solve it by yourself. I will also put the code, but I don't know if because the code is written with by me, so I have used the variables, and like it's my thought process that has gone into the code. So maybe, I don't know, it will be helpful for you all. But if you need, tell me in the comments and I can post the code later. But I have tried to just explain it in a way on a simple note-taking app, so that it will give you the intuition behind, like that will help you to get started to solve the problem. And that is very important. Like if you take my solution directly, then it's fine. It is like whatever I do, you will also do the same. But point is, if you understand the logic, you can try implementing yourself, because every one of you, I think, I must be sure you must be knowing the programming languages and you can implement it. Maybe you can implement it even better in a faster runtime. And this question will use the union find data structure, and that I'm not discussing in this video. Like I'm not discussing the union find data structure in this video. I'll see, because when you see that question, right, it is not complete first time, it is not evident that it will be used union find. But once you like, I hope you have to see the practical side of it, right? Like how it relates to the union find, and then okay, oh wow, it just gets solved. So let's get along and start with the problem solving. And I will, and this is just after this. So this is a small screencast. If there is any problem, let me know. Hi guys, so the problem states that given two arrays of words and an array of pairs, we have to find out if word 1 is similar to word 2. Okay, and how we need to figure out that is from the pairs we have. You can see the pair of words here, pair of words, right? From that we have to somehow figure out this one and what 2 are similar. And the relation, the problem statement states that the relation can be symmetric as well as transitive. What that means is, you can see here, if great is related to good and fine is related to good, that means great is also related to fine. So looking at this, and you can see the pairs, and somehow we have to relate it to the words, right? And from this, it is somehow clear that we can use the union find data structure for this. Means it's directly we cannot use, but if we convert it in such a way that it represents a union find data structure, then it will be very nice. So how we can do that is, actually we are going to see that it will be exactly using the same union find data structure with some minor tweaks. Okay, so what we can do is just a thought that the pairs could be is like the complete set of words we can always have, right? So like never it is like the complete universe of words. Okay, so what we'll do is first we'll try to make uh, a bijection map. uh, Bijection map, this is nothing but a fancy term of saying that each word will have a number or id, you can say, attached to that, so that we will convert this into a form that union find data structure understand, so that will be easy for us. For example, let's say so what I mean is, and by intuition you can see, you can just go over each of the pair and like each of the words for each pair and then push it into a map, where the map structure would be like a string with an id. Okay, and it will create a map. For example, I just wrote a code and ran through it, and the bijection map that it generated was like this. Like, okay, so this is the complete bijection map that I generated right now. Okay, and this is actually I'm taking from the debugger. As you can see, it is a map, so we don't have any order to that, and probably we don't know, and that's because it will make our accesses very fast. So this is the bijection map. So what we did is we just converted this the list of pairs into a map, and each map and the map has like just we need one instance of that word, right? We don't want multiple instances. For skill we have 5, for drama we have an id assigned called 3, so every unique word in the set will have one id. Okay, so now what do we do once we have the id? So now we can actually use our union find data structure, and the kind of union find algorithm that I am using would be the union find with path compression and weighted. So it will make it very fast. It will run in the order of log n, and it's very fast. You can just look about the amortized running complexity, and I'll just quickly explain how that works. So let's say there are multiple disjoint sets. Disjoint sets mean multiple separate elements. So right now these things are pointing to themselves. Okay, so let's say if I attach this to this, and let's say I attach this to this, and this thing is attached to this. Let's say we called it as 1, this is called 2, maybe, or sorry, 3, I say 4, and this is 5. So you can see 1 is connected to 2, 2 is connected to 3, 4 is connected to 5. So these are two different so this is why it is called disjoint sets, because this is a forest of sets. Okay, now what we'll do is, what this means is path compression. So let's say I want to say find 3. So when I say find 3, I have to find the parent of 3, that is 1. When I say parent of 5, I have to find I'll get 4. But the point is, you can see when you say a find operation, right? So find operation has to go through this long path, this whole path, to find out which this is. So what we can do is, when we are doing the first find operation, right? So actually we will see when the code runs, it will try to suppress as it goes along. So the idea is, when you are searching for 3, 2, 1, first time it will run in the order of n, but after that it is a constant time. Why? Because first you find the root, and in another loop what you do is, in that part, now once you got the loop, first get the root, then set all the nodes in path to root directly. That means this will get converted to like this. After that, any point in time, you just if you want to query anything from this set, it will just give you in O of 1 time. Okay, the same applies for anyone. So, and what about the weighted? Weighted is just nothing. It's like when you are doing a union, your union find data structure will have actually two arrays. So you have this map. This map will point to an ID array, which is actually like you can see it as first it is pointing like 1, 2, 3, 4, 5. Blah 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 like this, and then it has something called the size array. By default the size is 1 for everything. Okay, so now when you are doing starting to do so the join operation, the union operation, first you will look at what, so you will look at this one, okay, this array to find the pairs. So based on that, so you will see, let's say here great and good. So great is this 0 and good is 1. Okay, so what we will do is we will join 0 to 1. Oh sorry, I don't have a 0 here. I don't have a 0 here. So 0 will join to 1, so the parent of I would be 0. Okay, parent of I sorry, your parent of 1 would be 0, like this. So once we have joined everything, now we have a great union find data structure, and for each of the words we just see do a find operation. We just do a find operation, and then we check if we find in the set, that is fine. If we don't find in the set, we just stop there and return false. So that's how we solve the problem of sentence similarity.